Hey everybody, well I'm really excited with the way lecture 21A went. I hope I can carry over this momentum into lecture 21B. This stuff is getting into the heart of the course. It's the culmination of everything we've done so far. The second half of lecture 21A might be especially good for you to go back and revisit if you didn't watch it yet already, because I introduced the ideas of eigenvalues and eigenvectors for linear systems of differential equations, looking for straight line solutions. I do continue that here in lecture 21B, except now with difference equations instead of differential equations. But there's connections between the two subjects. That's what I live for, is that kind of thing. We'll also look at applying the rank theorem, which I talked about in lecture 20B, to systems of linear algebraic equations briefly at the beginning of this lecture. Let's jump ahead to the linear algebra slides now. Again, the first slide is going to be about the rank theorem. Recall, first of all, the definition of what the rank of a matrix is. By definition, the rank of a matrix is the dimension of its column space, okay? Which would be the same as the dimension of the image of the corresponding linear transformation. Okay, so we do want to be able to think back and forth between matrices and linear transformations. The column space of A, as we've talked about a lot, is the span of all the columns, the set of all linear combinations of the columns of A. That's the definition. There's nothing to prove there. The rank theorem, which is also known as the Rank-Nullity Theorem, says something specific that can be proved. Let A be an m by n matrix, so m rows and n columns. Then you can conclude that the dimension of the row space is the same as the dimension of the column space. The rank of A, defined to be the dimension of the column space, also equals the dimension of the row space, the set of all linear combinations of the rows of A, the span of those rows. They are row vectors, though I could certainly relate them to corresponding column vectors. These dimensions are the same. That's what that says. And that this also equals the number of pivot positions in A if you do row operations. And most importantly here, the rank of A plus the dimension of the null space of A, which is called the nullity of A, equals n, and is the number of columns. And would also be the dimension of the domain of the corresponding linear transformation. Remember, if A is m by n, that means the corresponding linear transformation is going to have a domain equal to Rn and a codomain equal to Rm. So I could think of it that way too. That's the n here. N is the number of columns of A. It's the same as the dimension of the domain of T, the corresponding linear transformation defined by T of x equals A times x. Let's now look at some applications. These applications are all kind of similar to each other. And what we're going to see is these questions that I'm going to show you. If you don't know the theory, you wouldn't know how to answer them, perhaps. But once you know this theory, once you know the rank theorem, then the answer comes pretty quickly. Suppose the solutions of a homogeneous system of 7 linear equations and 8 unknowns. Well, 7 and 8 are kind of arbitrary. I could have picked 70 and 71, as long as the number of unknowns is one more, are all multiples of one non-zero solution. Multiples of one non-zero solution. It's a homogeneous system. Think about that. What would that mean? What are we talking about here? Especially with regard to the null space of A. Question is, will the corresponding non-homogeneous system, non-homogeneous, be consistent no matter what the right-hand side numbers are? RHS means right-hand side numbers for the system. Okay, so yeah, if you don't know the theory, you'd be looking at this and like, I have no idea, right? That's the way it feels. But take it step by step. What do we have going on here? 7 linear equations and 8 unknowns means the corresponding coefficient matrix A is going to have 7 rows and 8 columns. So 8 is the value of n. That's the value of n here, and that would also be the dimension of the domain of the corresponding linear transformation. The linear transformation would go from R8 to R7. You switch around the numbers there. If A is 7 by 8, you go from R8 to R7. All right? So that's the basic thing here. All solutions are multiples of one non-zero solution. What does that mean? That means the null space of the matrix, the kernel of the corresponding linear transformation, must be one-dimensional. The dimension of the null space, the nullity, that's what the nullity means, that's the dimension of the null space, that's a definition, has to equal 1. This stuff implies that the nullity, which again by definition is the dimension of the null space, must equal 1. Now use the rank theorem, this last equation. N is 8, nullity is 1, solve for the rank. That means the rank must be 7. These two facts, here and here, by the rank theorem implies that the rank of A, not rand, but rank of A, dimension of the column space of A, must be 8 minus 1, 7. In other words, the rank of A is the dimension of the column space of A, which is the same as the dimension of the image of the corresponding linear transformation. In other words, T must be onto. T is onto. And what does onto mean? It means for every point in the codomain, there's something in the domain that gets mapped to it. The answer to this question about consistency must be yes, because T is onto. The answer is yes. The answer to the question. Is the system consistent no matter what the right-hand side numbers are? Okay? If the dimension of the null space was 2, then the rank would have to be 6. T would not be onto, and so then the answer would be no, it's not necessarily consistent no matter what the right-hand side numbers are. Cool. Using theory to answer down-to-earth sounding questions that you might be interested in. By the way, large systems of many equations and many unknowns do occur plenty in applications of linear algebra. You might even say it's the most important applications of linear algebra. Even hundreds of equations and hundreds of unknowns, or maybe even thousands of equations and thousands of unknowns. Second one, suppose we have a non-homogeneous system, with 13 equations and 15 unknowns. It's got 2 free variables. That sounds kind of like what I was saying there. Is it possible to change the right-hand side numbers to make the new system inconsistent? Kind of like what I was saying, when the null space is 2-dimensional, if we got 2 free variables. In fact, yes, the number of free variables I have mentioned a couple lectures ago is the same as the number of elements in a basis for the null space. That means it's the dimension of the null space. It is the nullity here. So n is 15. The nullity must be 2. Right, it's a 13 by 15 system. A is 13 by 15. N is 15. Therefore, the nullity is 2. Therefore, by the rank theorem, the rank must be 15 minus 2, must be 13. The corresponding linear transformation maps from R15 to R13. Because the rank is 13-dimensional, that means T's got to be onto again. We were talking about a non-homogeneous system at the start, so you might have been thrown by that. It's got 2 free variables. That would mean that if we considered the corresponding homogeneous system, that it would still have 2 free variables. They'd be the same variables, in fact. Yes, the dimension of the null space is 2. The nullity is 2, if that was a question for you. Last question here. Is it possible for a non-homogeneous system of 11 equations and 10 unknowns? So now we have more equations than unknowns. The other examples we had fewer equations than unknowns. To have a unique solution for some set of right-hand side constants. Second question, is it possible for such a system to have a unique solution for every set of right-hand side constants? So A here is 11 by 10. 10 is what n is in the rank theorem. The corresponding linear transformation goes from R10 to R11. should be able to answer the questions right away intuitively. Such a linear transformation, I emphasized already, from a lower dimensional space to a higher dimensional space cannot possibly be onto. The rank theorem gives us a more rigorous reason for that. So while it is possible for it to be, well, it is possible for it to be one-to-one though. You might even say it's likely to be one-to-one. So it is possible to have a unique solution for some set of right-hand side constants. The answer to the first question is yes. But not for every set of right-hand side constants, because that codomain is higher dimensional than the domain. This can't possibly be onto. Again, a little bit more rigorous reason. You can base it on the rank theorem. N is 10. That's going to mean that the rank of A, using this equation, must be 10 minus the nullity of A. In other words, the rank of A must be less than or equal to 10. It can't possibly be bigger than 10, because you're subtracting the nullity, which can't be a negative number. The nullity's got to be 0 or 1 or 2 or 3, etc. So the rank's got to be less than or equal to 10. In particular, it can't equal 11. Rank A cannot equal 11, so the column space cannot be 11-dimensional. The image of the corresponding linear transformation cannot be all of R11. T cannot be onto. It could be one-to-one, so there could be a unique solution for some set of right-hand side constants. But it cannot be onto, so the answer to the second question is no, there's not necessarily a unique solution for every set of right-hand side constants. There will be plenty of right-hand side constants where the system is inconsistent. Okay? So the rank theorem allows us to make our intuition a bit more rigorous. All right, for the rest of this lecture B, we're going to look at difference equations. And again, like I mentioned at the beginning, this is very analogous to what I did in the second half of lecture 21A with differential equations. I introduced eigenvalues and eigenvectors. The same eigenvalues and eigenvectors ideas come up in this part of lecture 21B. In fact, it's the same matrix that I used in lecture 21A, but now for a difference equation instead of a differential equation. Here we have a difference equation, a linear, two-dimensional difference equation. Don't be bothered by the fact that when I do difference equations, I use lowercase boldface x for my vectors, but when I do differential equations, I use uppercase boldface y's. Don't worry about it. It's not a big deal. I'm kind of doing it just to separate the two subjects in a sense. Boldface vector x has components little x n and little yn, subscript of n. This is a difference equation. It's a times xn minus 1. Of course, I also could mention the corresponding linear transformation. T of x would be a times x, but I'm not. Same matrix as in lecture 21A. 1, 3, 2, 2. It's going to have the same eigenvalues and the same eigenvectors. So that's why it's beneficial to look at 21A first, second half. Go there. If you multiply this out, you can write the right-hand side of the difference equation like this. How do you solve difference equations? You iterate this. You use it over and over again. That's analogous to integrating a differential equation. Yeah, this is the same matrix. If it's the same matrix, does that mean there are straight line solutions just like in lecture 21A? And are eigenvalues and eigenvectors still relevant? The answer to eigenvalues and eigenvectors being still relevant is a definite yes. The answer to there being straight line solutions is a partial yes. There will be solutions, discrete set of points that, well, it goes on forever and ever, it's an infinite set, a sequence, that do lie on straight lines, but they are points that are separated. They're not a continuous curve. They're not a parametric curve. So the answer to this straight line solutions is kind of. The solution to this system is easy, in a sense. Is it? Back in lecture 14b, I essentially derived this equation, though I included the linear transformation in these lines, the t. Now I'm not worrying about writing t in there anywhere. You solve the difference equation by iterating. xn equals axn minus 1. But xn minus 1 is a times xn minus 2. By the associative property for matrices times vectors, I can move these parentheses to being around the a times a, which means I can write it as a squared. But then, hey, xn minus 2 is a times xn minus 3. Maybe I should have put parentheses there. And then I could move the parentheses again. A squared times a is a cubed. Etc. The pattern indicates that in the end we get a to the nth power times x0, where x0 is the initial condition point, whatever that happens to be. But this does beg a question. So this is easy, in a sense. That's integrating the difference equation. Very easy to do, especially with it being linear here. But it does beg a question. How do we compute a to the n power? You might guess that you take all the entries of a and raise them to the same power. But that would be wrong. The answer is not just to raise all the entries of a to that power. Unless, very importantly, A happens to be a diagonal matrix. We actually did see before, in lecture 14b, I think, that if A is a diagonal matrix, you can find a to the n by just raising the diagonal numbers to that power, and effectively the off-diagonal numbers to that power too, because they're all zeros. But you can't do that with this matrix. It doesn't work. We'll see. The fact that you can do it for diagonal matrices is going to ultimately be how we relate all this stuff to change of basis, which we've also talked about recently. We're not going to relate it in this lecture. It's too much for this lecture. But ultimately, not sure how many lectures in the future here, we're going to relate non-diagonal matrices to, if we can, diagonal matrices. Turns out you can't always do that. Diagonal matrices, and that's going to involve a change of basis, a change of coordinates. And that's the main application of linear algebra to differential equations and difference equations that I've emphasized all along. But we're not quite there yet. So what can we do? We could try looking for a pattern as a first attempt. Try raising a to higher and higher powers and see if there's a clear pattern to the entries. We might cross our fingers and hope or pray that there's a clear pattern. So what's a squared? It's a times itself. Double check this calculation. 2 by 2 matrix times a 2 by 2 matrix is also a 2 by 2 matrix. The entry in the first row and first column is going to be the dot product of the first row of the matrix on the left with the first column of the matrix on the right. Now they're the same matrices in this case, but in general that's what you have to do. So we get 1 times 1 plus 3 times 2. 1 plus 6 is 7. For the upper right entry, first row, second column, dot product of the first row on the left with the second column on the right. 1 times 3 plus 3 times 2 is 3 plus 6 is 9. Lower left entry, second row, first column, dot product of the second row with first column. Second row on the left, 2 times 1 plus 2 times 2. 2 plus 4 is 6. Finally, lower right entry, second row, second column, dot product of the second row on the left with the second column on the right. 2 times 3 is 6, plus 2 times 2 is 6 plus 4 is 10. All right, I'm also going to compute a cubed and a to the fourth, but I will not take the time to double check verbally everything that you see here. You may want to pause the video if you feel like you need practice at this to double check these numbers. I don't see a completely obvious pattern. Do you? I mean, there are patterns, kind of interesting patterns actually. I mean, with a squared, 7 is 1 bigger than 6, and 9 is 1 less than 10. And with a cubed, it sort of switches around. 26 is 1 bigger than 25, and 39 is 1 bigger than 38. And with a to the fourth, it kind of switches around again. 103 is 1 bigger than 102, and 154 is 1 bigger than 153. Interesting. So there's a pattern there. But does that mean it helps me find the formula for these things as a function of the power? That's not so clear. I mean, if you want to pause the video and work on it for an hour or two, you can. It'd probably be pretty hard. So what do we do? Second try. Guess some solutions, just like we've done with differential equations and difference equations before. The differential equations, way back in lectures 1, 2, 3 or so, when we have a scalar linear equation of the form dy dt equals a times y, the general solution was c times e to the at, where c is arbitrary. And if we have a generic initial value problem with initial condition y0, we wrote the unique solution of the initial value problem like that. If I add that initial condition, y of 0 equals y sub 0. The corresponding analogous difference equation we can write as yn equals, I used a k way back when, like that. I also did it initially with an n plus 1 there and an n there, but it doesn't matter, it's still the same idea. And if our initial value is y0, which I don't need to really write separately, we could write yn equals, we saw y0 times k to the n. By the way, we could write y of t here as well. T is a continuous variable, arbitrary real number. N is an integer, starting with 0, then 1, then 2, then 3, then 4, etc. But actually, we could use negative values for n as well. Then it actually would still solve the difference equation. We've never done that before, but we could. So, are we inspired by this at all? Are we? Maybe we should try something like this. Maybe just the k to the n part. But wait a minute, these solutions can't be scalars, they got to be vectors. Maybe I take k to the n times a certain vector. I'm not going to call it k to the n, I'm going to call it lambda to the n. Lecture 21a, I introduced eigenvalues and I called them lambda. Same thing here. The lambda is going to be an eigenvalue of a. We will ultimately see here very shortly. Guess lambda to the n times the vector x0, which in components would be this, and you also could multiply the scalar lambda to the n into each component if you wanted to. Analogous to this, except the k is replaced by a lambda, and the y0 is replaced by the vector x0, and they also switch around the order. Just by tradition, traditionally, you put the scalar on the left side of the vector. So let's just see. Again, a lot of this course, in the linear situation at least, is educated guessing. And I'm educating you on what to guess. If you forget in the future, maybe you can sort of try to rethink it through from scratch. When we substitute into the right-hand side of the difference equation, we get this. What is the right-hand side of the difference equation? The difference equation we're talking about here is vector xn equals a times vector xn minus 1. The right-hand side is a times xn minus 1. I'm substituting that in here. But you say, wait a minute, that's not the same. Well, it is the same if you change the subscript. If I replace this n with an n minus 1, then I'd get a lambda to the n minus 1 here times x0, which is what I got here. So it is using that. And this is kind of similar to what I did in lecture 21a. I could factor the scalar out in front like that. And I could just write it in scalar matrix vector form like this, or I could plug in what a is and write it like that if I wanted to, but this is probably more important to focus on it this way. That's the right-hand side. What about the left-hand side? The left-hand side is just xn, which equals this, because that's what I'm guessing. So I want to essentially set this equal to this, and that's what I do here. And now simplify. I guess I could divide both sides by lambda to the n minus 1. Well, at least if lambda is non-zero. Actually, eigenvalues can be 0. We'll talk about that later. Eigenvectors, don't take those to be 0. You want non-zero vectors for eigenvectors. But eigenvalues can be 0. Remember that for the future. But in this derivation, I'm assuming lambda is non-zero. And I get this equation. Hey, that looks familiar from lecture 21a. where I wrote is A times V equals lambda times V. Lambda was an eigenvalue, V was an eigenvector. The x0 is playing the role of the V. So you might be wondering what initial points, what initial conditions are possible to find, and what values of lambda are possible to find where this might be true. Just as in lecture 21a, this is going to have non-trivial solutions if I think about it this way, just like I did in 21a, if and only if the determinant of that matrix is 0. Remember again, by the invertible matrix theorem, when you've got a square matrix, and you're looking at the homogeneous system of that matrix times a vector equals 0, that has only the trivial solution. The kernel is 0, the null space is 0, if and only if the determinant of the matrix is non-zero. But that also means that you're going to have non-trivial solutions, non-zero solutions for x, if and only if the determinant of this matrix is 0. I called this the characteristic polynomial back in lecture 21a as an exercise for you. If you're deciding you're not going to watch lecture 21a, it ends up for this matrix, capital A, right here, to equal lambda squared minus 3 lambda minus 4, which can be factored as lambda plus 1 times lambda minus 4. And that means the eigenvalues, which are the lambda values that make this have a non-trivial solution for some x0, are -1 and 4, the roots of this quadratic polynomial. Lambda can be -1 or 4. Those are the eigenvalues. And the corresponding eigenvectors then are found by plugging in those values into this equation, and two separate systems to solve, one when lambda is -1, one when lambda is 4, solving for non-zero, non-trivial solutions of this system, this homogeneous system. And if you do it right, you should be able to find them. And again, I did that in lecture 21a. Yeah, hey, eigenvalues and eigenvectors, lecture 21a, and what did I get? I get these two vectors. Let's actually check this in a different way here in lecture 21b. If you know the eigenvectors or the proposed eigenvectors ahead of time, you can check. If you know the eigenvalues and the eigenvectors ahead of time, you can check that they work by checking the equation A times the vector equals lambda times the vector. Left-hand side equals right-hand side. So A times V1 here is 1, 3, 2, 2 times V1 is -3, 2. Multiply, I'm going to get -3 plus 6, and then also a -6 plus 4. That's 3, -2. And look at how these are related. That's -1 times the vector -3, 2. Lambda is -1 times V1. That's, say, lambda 1 times V1. And you can do the same kind of thing with lambda 2 and V2. Take A and multiply times V2. The fact that lambda 2 is 4 means you're going to get the vector 4, 4. 4 times 1, 1. Try it. It works. What do we do with differential equations at this point? We wrote down a couple solutions and we said, hey, they're linearly independent. And we said the solution space as a vector space is two-dimensional, and therefore the basis theorem allowed us to write it, the general solution as a linear combination of those two particular solutions. We can do the same kind of thing here. Notation's a bit funny here. X sub 1 sub n is a function of n. Double subscripts here. The 1 just says it's going with V1 and lambda 1. That's all the 1 means. It's lambda 1 to the n power, lambda to the n, like we had in the last slide, I think. Maybe 2 slides ago, I don't remember for sure. Times V1, which is this. And x sub 2 sub n goes with V2 and lambda 2. lambda 2, 4 to the n times v2. 4 to the n times 1, 1. And these two functions of n are linearly independent. They're not scalar multiples of each other, which again is the simplest way to think about it with two vectors. Of course, when you've got 3 or more vectors, then it gets harder to think about linear independence. What would happen if you graph these? Could you graph them? Yeah, you can graph them in a plane, say an xy plane. Focus on x2n first. 4 to the n times 1, 1. No matter what n is, that's a scalar multiple of 1, 1. As a point, it's got to line this line through the origin with a slope of 1. When n is 0, 4 to the 0 is 1, you're at the point 1, 1. That would be the point, I guess, using this notation, x2 sub 0. When n is 1, be 4 to the first power times 1, 1, 4 times 1, 1, which is going to be 4, 4. x1 as a point, or x2 sub 1, as a point is 4 times further away from the origin. What about when n is 3? 4 cubed times 1, 1. 4 cubed is what? 64? I think. Yep. Right? Okay, yep. 64, 64. You'd be off the chart. And as 4, you'd be even further away. These points would go off to infinity. But they'd all be on this line. They're all on a straight line solution, you might say. Well, not in the same sense as lecture 21a. I could also plot this even for negative values of n, then I get 4 to negative powers, which are positive numbers. Like, for example, when it's 4 to the negative 1, I get 1/4, 1/4, and it would be going closer to the origin as you let n go backwards toward minus infinity. With this one, you're going to be parallel to the vector negative 3, 2. Something about like this, say. When n is 1, you're at the vector, when n is 0, this is negative 1 to the 0, which is 1. You're at the point negative 3, 2. So right here, that would be x1 sub 0, x sub 1 sub 0. When n is 1, negative 1 to the first is negative 1, times this vector is positive 3, negative 2. You're going to be at this opposite point across the origin here. Hey, and I guess when n is 2, you're back where you started. This is going to bounce back and forth between these two. This is also going to be x1 sub 2. This is also going to be x1 sub 3, etc. You're always going to bounce back and forth along that line. That kind of behavior doesn't happen with differential equations. You can't bounce back and forth in a phase plane for differential equations. Interesting. Different kinds of things can happen with difference equations, even though similar things happen as well. Yeah, if you graph the points, these sequences, also called an orbit sometimes, for fun, because they sometimes can orbit around a point, like a planet going around the sun. Not always, as they don't here. In the plane as n varies. They will all, in each case, lie in the same line through the origin. They're not the same line here. Two different solutions lie on two different lines. The solution space as a vector space is two-dimensional. This takes proof. I'm not proving it. Not sure if I will prove it at some point or not, or at least talk about a theorem that implies that. I probably will talk about a theorem that implies it, but I'm not sure if I'm going to prove that theorem. Therefore, by the basis theorem, if you've got two linearly independent solutions, they're going to span. They're going to be a basis. So an arbitrary solution, any solution, is a linear combination of them. That's what I have here. So much coming together here, which can be written this way. And just like in 21a, you could take that formula and solve any initial value problem that you want based on any vector x0 that you start with. Now, it was at this point in lecture 21a that I stopped, but I don't want to stop here in lecture 21b. And not just because we theoretically have more time, but there's something else interesting to figure out here. I'm going to try to solve a generic IDP, figure out what K1 and K2 are in terms of an initial point whose components are x0 and y0. Plug that in for K1 and K2 and try to simplify, and maybe something interesting will be seen. So take an arbitrary initial value problem. I'm thinking of this as fixed. So I will be talking about a particular solution, you might say, for a fixed point. That point's not necessarily on one of these lines. In general, it won't be. And so in general, the points will not necessarily be on the same line through the origin. Plug in n equals 0 to our general solution to solve for K1 and K2 ultimately. The initial condition, vector x0, y0, an arbitrary initial condition, I could write as a vector. I could also say, based on the solution from the previous slide, that that's K1 lambda negative 1 to the 0, negative 3, 2, plus K2 4 to the 0, 1, 1. Of course, negative 1 to the 0 and 4 to the 0 are 1, so this simplifies to this, which, if I want, I can write as this matrix times this vector. I want to solve for K1 and K2 in terms of x0 and y0. Most typically, we use row operations to do that, right? Go to reduce row echelon form. For fun, I'm going to use an inverse matrix. There we have it. And more practice with inverse matrices. I can take this equation, this vector equals this matrix times this vector, and multiply on the left by the inverse of this matrix, which will exist because its determinant is non-zero. Its determinant is negative 5. So I can write it this way. K1, K2 is the inverse of this matrix times this vector x0, y0. The shortcut formula for the inverse matrix is to take 1 over the determinant. Determinant is negative 3 minus 2, which is negative 5. And then for the entries of the matrix itself, for the 2 by 2 case, you swap the numbers on the main diagonal. The negative 3 and the 1 get swapped. And you put negative signs in front of the numbers on the off diagonal. The 1 and the 2 get negative signs put in front of them. If one of them had happened to be negative, like if that had happened to be negative 1, then I'd get negative of negative 1, which would make this a positive 1. Simplify, you get this. So I guess K1 is this in terms of x0 and y0, and K2 is this in terms of x0 and y0. You should take the time to double check that. Therefore, the unique solution of the generic IVP can be written by plugging those in for K1 and K2 to get this messy looking thing. And now I'm about to show you how you can rewrite this in a way that may blow your mind, or maybe not, to find a to the n power. Remember way back when I said the solution of this difference equation is xn equals a to the n power times x0. No matter what a is. Well, it's got to be a square matrix here. The dimension of the rows and columns have to be the same. The linear transformation has to go from Rn to itself. In this case, R2 to itself. Probably shouldn't have said Rn because that messes up with that end. Rm to itself. So there's the equation from the bottom of the last slide. Let's combine this all into one vector. How? Multiply this crazy looking scalar into each component of this vector, and this crazy looking scalar into each component of this vector to get the sum of two vectors. Then combine those two vectors into one, add the two vectors by adding component-wise, and then let's regroup in such a way that the x0s are together and the y0s are together so that I can factor them out. And if you check it, you get this. For example, where does this one come from? Take negative 1/5 x0 times negative 1 to the n times negative 3. The negative 3 and the negative 1/5 give you positive 3/5, but I still have the negative 1 to the n, and I'm factoring down an x0 because I get also another x0 from Here, 2/5 x0 times 4 to the n times 1. 2/5 times 4 to the n, factor out the x0. This is a vector here, not a not a 2 by 2 matrix, it's a 2 by 1 vector. This plus that and this plus that. 2 entries, 2 components to this vector. However, I could write that as a linear combination. x0 times a certain column vector plus y0 times a certain column vector. And by the definition of a matrix times a vector, that's a linear combination of the columns of a matrix. What matrix? This matrix here. That is a 2 by 2 matrix. 1 1 entry, 1 2 entry, 2 2 1 entry, and 2 2 entry. First row, first column, first row, second column, second row, first column, second row, second column, times x0, y0. That's the definition of a, in this case, 2 by 2 matrix times a 2 by 1 vector. Linear combination. I skipped a step. I'm imagining the step that way. And wait a minute, I guess this last thing that I just underlined there equals a to the n times, well, if I include this part, equals a to the n times x0. It must be. If what I said here is true, that must be the case. That must be the pattern that I said you could take an hour or two to guess if you wanted to, but you may not be successful. We've found the pattern. That's significant. Is it really right? Did it really work? We might want to check it with those powers of a that we computed before. Let's consider the a to the 4th power. It was this matrix. If you plug n equals 4 into the last expression in the previous slide, so all these 4s that you see in the powers here, those were n's on the previous slide, but now I'm replacing n with 4. Simplify. 4 to the 4th is 256 times 2 is 512. This is a plus 3, so I get 3 plus 512 over 5. You can check the other ones too. 4 to the 4th, again, is 256 times 3. You can check as 768. Simplify, and you get the exact same answer. That's just beautiful. I think it's beautiful. I think it'd be good to end there. Yep. Thanks for watching.